Very well. Let's do an example of the photoelectric effect, taking into account the conversions we talked about in terms of energy, wavelength, energy per photon, and energy per mole. All right, so here we're being told that we are shining a metal surface with light of 5.98 times 10 to the 15 hertz frequency. And the resulting electrons come out with kinetic energy of 250 kilojoules per mole. What we want to find out is the wavelength of the work function of the metal. Now, one thing to be kept in mind is the work function or ionization energy is the same thing as potential energy. So we're basically going to go after the potential energy of the metal and ultimately end up in wavelength units. Now you might be tempted based on what we have here. We have hertz for the light, we have kilojoules per mole for the kinetic energy, and we want wavelength. You might be tempted to change the hertz and the kinetic energy to wavelength units. Do not do that. The reason being is that wavelength is not directly proportional to energy. It's actually inversely proportional. So you can't just add up wavelengths or subtract wavelengths the same way that you subtract joules from each other or subtract frequencies from each other. So for this particular problem, you will have to first find out the energies of light and of the electron in terms of joules per photon. And from there, we'll go ultimately to wavelength. Alright, so in order to do this, I'm going to subdivide the screen to these 8 different cells. Here on the left, I'm going to show the equations that we need to use, and over here, I'll perform the actual operations. So first things first, we know that there is light with 5.98 times 10 to the 15 hertz. Now the fact that this is the light being shined on a metal implies that the 5.98 times 10 to the 15 hertz is the total energy of the system, given in terms of frequency. So what we need to do is say, okay, we have frequency for the light. We also know that for frequency, we have a relationship that allows us to get the energy per photon. So that's what we're going to do right here. We're going to get the energy per photon for the light source. And so we multiply Planck's constant, 6.626 times 10 to the negative 34 joules times second, by the frequency, 5.98 times 10 to the 15 hertz, or per second. Here, the seconds are going to cancel out, and you'll end up with units of joules. And I would recommend that you do use parentheses for the exponential number. So parentheses 6.626 times 10 to the negative 34, close parentheses, times, open parentheses, 5.98 times 10 to the 15, close parentheses, and press enter. You should end up finding out that the total energy is 3.96 times 10 to the negative 18 joules. Okay, so we found out the energy in joules for the light source. This is the total energy of the system. Now in the problem, we're being told that the electron comes out of the metal surface with an energy of 250 kilojoules per mole. This is the kinetic energy of the electron. And since the units are in kilojoules per mole, the only place we can really go is to joules per photon, also known as regular joules. Alright, so we're going to start with that. 250 kilojoules divided by 1 mole. So I'm now rewriting it as a fraction, keeping the kilojoules with the number and placing the moles in the opposite end of the fraction. And pretty much what I'm going to do is I'm going to change the moles to photons, because we know that in 1 mole of photons there is Avogadro's number worth of photons, right? And notice that we have moles on the bottom, so we place moles on top. The moles will cancel out. And now we're going to have kilojoules divided by photons. Almost there, but not quite. What we need to do lastly is to change the kilojoules to joules, and for that we divide by 1 kilojoule multiplied by 1000 joules. This will allow the kilojoules to cancel out, and now we have units of joules per photon, which is the same thing as just regular joules. In this particular problem, it is of utmost importance that you do use parentheses, specifically because we have an exponential number on the denominator. So I would recommend doing the following. Enter 250 in your calculator, divide by, open parentheses, 6.022 times 10 to the 23rd, close parentheses, press enter. The resulting answer, multiply by 1000, and you should find out that the kinetic energy of the electron coming out of the metal is 4.15 times 10 to the negative 19 joules. This is the kinetic energy. Okay, now that we have both of them in units of joules, we basically use the setup that total energy equals kinetic plus potential energy. This is the setup of the photoelectric effect. And right here we're looking for the work function, aka the potential energy. So we will subtract the kinetic energy from both sides. Potential energy will equal total energy minus kinetic energy. Total energy is 3.96 times 10 to the negative 18, so here we have it. Kinetic energy is 4.15 times 10 to the negative 19. There we go. And upon subtracting them, you should find out that this equals 3.54 times 10 to the negative 18 joules. It might not be a bad idea to use parentheses for this operation, but I believe your calculator should be able to handle this calculation without miscommunication. All right, now the potential energy that we got is in joules, but what we want is the wavelength of the potential energy. So here, now we get to trace our steps backwards using Planck's equation, specifically the one where energy equals hc over lambda, lambda representing the wavelength of the light source, in this case the potential energy of the electron to the nucleus of the metal. So what we do is simply cross multiply lambda with the energy. That will yield the following equation. Lambda equals hc divided by energy. So now we're going to multiply Planck's constant by the speed of light and divide it by the potential energy, which is 3.54 times 10 to the negative 18 joules. Alright, so we're going to have the following setup. Okay, wavelength equals 6.626 times 10 to the negative 34 joules times second times 2.998 times 10 to the 8 meters per second divided by 3.54 times 10 to the negative 18 joules. You can see right here that the joules will cancel out, the seconds will cancel out, and you'll end up with units of meters. Although not specifying this problem, I am going to convert the meters to nanometers. In future problems though, I'll probably tell you, give me the wavelength in angstroms, or give me the wavelength in micrometers, or picometers. So be ready with your conversion analysis, because it will play a role here. But upon multiplying by 10 to the 9, we will change the meters to nanometers in this problem, and multiplying Planck's constant by the speed of light, pressing enter, divided by open parenthesis 3.54 times 10 to the negative 18 close parenthesis, pressing enter, and then multiplying by 1 times 10 to the 9, pressing enter, should yield a value of 56.1 nanometers. And similar problems of this sort are going to be seen in future assignments and future exams, but I will introduce a few extra units, something that's going to happen on the next lecture. But this is just to give you a flavor of how the photoelectric effect can actually be used in order to play around with the units, the conversions, and ultimately with the idea that the total energy is the sum of kinetic and potential energy together. Okay, with that, we'll continue on the next video.